Moving on, our next event is a keynote. Dr. Christof Wunderlich is the Chief Science Officer at eleQtron, and he's going to speak about ion trap quantum computers using magnetic gradient-induced coupling, MAGIC. We've got a new acronym, between qubits. MAGIC dramatically reduces the demands on laser performance and makes coherent qubit control exclusively with microwave fields possible. So, Dr. Christof, are you here? Yes, hello? No? This is where I sing the Jeopardy theme. Dun, 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 dun. Check with the crew. Take a minute and wait. Hopefully he'll appear. I actually met him earlier this morning, so I know he's here somewhere. Maybe he had an emergency client meeting. Takes precedence. He's here, yeah. So hang on. We'll be back to you in a moment. We found him. I think the dessert was too rich, the sugar rush, I don't know, something happened. Anyway, they're putting a headset on him. So you're looking forward to learning about this. I haven't heard of this technology, MAGIC, huh? Magnetic gradient-induced coupling between qubits. So it'll be interesting to hear, comparing and contrasting with what Dr. Montasai was talking about, graphene this morning. So new innovative approaches for communication, connecting qubits, networking at a meta level. So, when he's approaching the stage, I'll cue the applause. Oh, and here he is, okay. Ladies and gentlemen, please welcome, late but not, Dr. Christof Wunderlich.
Right. So, yeah, thank you very much for the organizers and for your attention. So I'd like to tell you a little bit about how we do magic quantum computing, and magic is not just something fancy, a fancy name. It stands for magnetic gradient-induced coupling, and it's a particular way of doing trapped ion quantum computing. So that's the, what I will be talking about for the next few minutes. Okay, quantum computer and applications. We heard many highly interesting things in previous talks and panels, so I'm not going to go into applications of quantum computing. I think most of us are convinced that this is highly interesting. So instead, I'll jump right to the next slide. And so I'd like to start my presentation with a short view on history of quantum physics. A very brief view to remind you of some, I think, important facts. So one can think of that quantum physics started at around 1900 with Max Planck. You know Max Planck's constant, that is, plays a central role in quantum physics. And then quantum mechanics developed very nicely, and then the first transistor in the late 40s, the first transistor was invented, which is based on quantum mechanical effects. And today that we're here and that we're using cameras and computers and everything, that's the crucial invention was the transistor and then integrated circuits and so on. And then another important thing that involves quantum mechanics is lasers. So again, this is one of the bases of our today's technology, as you of course know. And okay, but these effects rely on collective effects of many particles or many quantum systems together. And so the new thing, and actually so Erwin Schrödinger, one of the founding fathers of quantum physics, he said even in the 1950s it's basically not conceivable to experiment to work with individual quantum systems. So that was not conceivable at the time, and this changed at a decisive date, so at the 17th of April in 1979, when for the first time a quantum particle was isolated and deterministically prepared and could be made visible. So this really changed the view on quantum physics to be able to experiment, not only think about, but to think about individual quantum systems, but actually do experiments with them. And today's quantum computing, sensing, communication is all based on using individual quantum systems. So that's an important thing. And the first quantum system that was observed was a trapped ion. And actually, so this was, the Nobel Prize was given to Wolfgang Paul and Hans Dehmelt for this achievement, for this trapped ion technique, only 10 years later, so which is a short span typically for Nobel Prize. And in 2012, David Wineland received the Nobel Prize for developing this further and doing fundamental investigations using trapped ions, to manipulate individual quantum systems using trapped ions. So, and of course, together with Serge Haroche, who did the same thing with photons. So individual quantum systems are essential for any quantum technology, and trapped ions are a particularly interesting thing. So, okay, so now I'd like to show you some trapped ions just for fun. So that's one of our traps that we operate on a daily basis. So you can see these individual ions as they pop into the trap. They fluoresce nicely, and then you can start controlling them. So this is a register of trapped ions. They nicely fluoresce and stay there for a long time and wait that you do interesting things with them, like quantum computing. And what I'd like to emphasize is the physics of these trapped ions is very well understood. So one of the impressive results of physics research is to have, yeah, this laser still doesn't work, 10 to the minus 18 systematic uncertainty in preparing an atomic clock. So the physics is extremely well understood of this system. Okay, so now we want to use trapped ions for quantum computing. And what do we need? First, we need qubits, obviously. So, and in trapped ions, two internal states of each ion are typically a qubit. You can also look for qubits for multidimensional systems. And the nice thing about trapped ions is that they are identical, always identical, whether you're here in Dubai or in Australia or in Germany. It's always the exactly same atom, and it has predictable properties and is always in perfect quality given. And okay, if you want to do quantum computing, first you need to initialize your qubit at the beginning of the algorithm, and you have to read it out at the end of the algorithm. This works with immense precision for trapped ions, so many nines here in these numbers. Okay, so that's the beginning and the end of a quantum algorithm. In between, you need to manipulate your qubits individually. And this also works extremely well with trapped ions, with many nines in the fidelity. And then you need to keep the quantum information. Ideally, you want to keep it for a long time in your qubit once you prepared it. And this is also, yeah, for trapped ions, this can be on the order of hours, which is extremely long compared to the gate times. Okay, so the necessary ingredients for quantum computing are very nicely fulfilled with trapped ions. But of course, that's not all. We talked so far about individual qubits. Now you have to have them interact in a deterministic way. And that's multi-qubit gates, for instance, 2-qubit gates, and they also work with extremely high precision, typically. And what's not so advantageous for quantum computing, I say advantageous because strictly it's not necessary. If you have perfect qubits, you can build a quantum computer, a universal quantum computer, but none of us has a perfect qubit, or you will need error correction at some point. And to do error correction, you need, okay, so I reversed the order here, apparently. So first I wanted to talk about connectivity. So you need conditional quantum dynamics between qubits to implement an algorithm, and high connectivity means you can speed up your algorithms and you can make deeper quantum algorithms. So these, the dark dots represent qubits, and the lines between them say that you can let them interact directly. And so with trapped ions, typically you can have all-to-all connectivity, which is very advantageous. Okay, so and then, yes, this is not the newest slides. Well, doesn't matter. Okay, so what I wanted to say before is about error correction. If you really think about scaling up, you need error correction at some point for a universal quantum computer beyond NISQ machines. And there you have to encode your physical qubits into logical qubits. And as has been shown with trapped ions, the ratio can be about 1 to 10, so 10 physical qubits for one logical qubit. And the ratio of coherence time to gate operation time, I already mentioned that, that's also unsurpassed in any other implementation. quick question. Does this time really apply that I'm seeing here? It says 3 minutes. Okay, so otherwise I would be... All right. Yeah. Okay. Very good. Thanks. Okay, so now comes the drawbacks. I told you how great ions are, and but these results I just showed you, these really impressive results, they are cherry-picked from many labs all over the world. So they are not performed on one system, but one group did the best readout, the other group did the best single qubit fidelity, and so on. So, of course, the ambition is to put this all together in one machine in the end. And so David Wineland, he prepared actually this slide here. So that's a view of his lab a few years before he got the Nobel Prize, actually. So he did these pioneering experiments on using also trapped ions for quantum computing. And he pointed out on this slide, so this is a room about this size from the first row of seats up to the stage, and yeah, it's filled with optical elements, with lasers and all kinds of stuff. And if you enter such a room as a non-physicist, you might be scared and also have doubts about scalability of such a device, and even Dave Wineland had doubts about the scalability of the whole thing. And one thing that makes it really difficult to scale up is, as David pointed out, is all this optics, all this lasers and all this stuff. So that's where magic comes in. So now I'm coming from the general view of trapped ions to our particular view of trapped ions, what we do at eleQtron. So this is, so if you take a close look at this lab, at this optical table with all its elements on it, you will notice that the signals that control your qubits, the ions, they are actually controlled by radio frequency signals. So by radio frequency, I mean anything between kilohertz and 100 gigahertz. So, and then on this optical table, these signals are converted into optical signals and then applied to the ions. And of course, all these optical elements on this, on this table here, they contribute to making your life difficult in achieving precise and repeatable operations. So what this magic method does is actually we, using this magnetic gradient-induced coupling, we can get rid of all the laser light for coherent control and instead control the ions directly using radio frequency radiation. So we can use the technology basically that's incorporated in your mobile phone. So there you have microwave signal generators, amplifiers, phase locks, everything you need. And that's sufficient to drive the qubits in trapped ions. Okay, so now I really need to know how much time there's. 5 minutes, okay. All right, so there's no cursor here, so how can I push this button? Well, okay, so yes, so how does this magic work? So I'll give you a classical physics explanation, so to say. So we have atoms that have a magnetic moment, just like a compass needle. And we put this, if you put this compass needle into a magnetic field, then it has a preferred orientation, as you all know. And and now you can put in energy into your needle by turning it around. So you flip your needle, you put energy in, and now the energy that depends of the needle depends on the orientation of the needle in the magnetic field. And classically, of course, you can have any energy. Quantum mechanically, you can only have two energies. So, and that's what we call qubit state 0 and qubit state 1. Okay, so and then you have a certain energy gap between these two states, and that corresponds to a certain radiation frequency that you can use to flip your qubit. Okay, so now we have two qubits, and they are not in a homogeneous field, but they have in an inhomogeneous field, so weak field on the left side, strong field on the right side. And then your qubit resonances are split in frequency instead of in position, as for different ions at different positions. They are now split in frequency, and you can address them extremely well with extremely low crosstalk, as you can read in this publication here, so I cannot go into the details now. So we demonstrated a world record low crosstalk in such a quantum byte. Okay, so addressing works very well. Single qubit operations work very well. Now, how do you get coupling between different qubits? So this magnetic field gradient again helps. So you flip the needle, and then you go from this lower slope to the upper slope. So the magnetic moment, your needle feels an additional force. It slides down this potential hill here, and it moves to a different position. And now imagine there are other ions there, and they are all charged, so they repel each other. And so this ion pushes away the other ions. They all change their energy, and that's how you get spin-spin coupling. So that's what you use for conditional quantum gates. Okay, that's as much physics as I wanted to tell you. Now I'll just give you a brief summary of our research results in many years of research. So we proposed this magic scheme, which now is implemented in various variations over the world. But we were the first ones to show that it really works. So RF signals instead of lasers. We can do this individual addressing with extreme precision, better than any other implementation. We have high connectivity that was demonstrated. We also move around ions in our traps with very high fidelity, so that's also an essential ingredient for scaling up. And we show that we can reconfigure our qubits between memory and processor qubits simply by applying radio frequency pulses. So that's research results, and now I'll come to the company. eleQtron, so this is the first quantum computer, Ruby is it called, of eleQtron. So this is now that artist's view that's in the middle, that's actually in the building of eleQtron. That's 10 to 20 qubit quantum computer that is also delivered to various research institutions. So that's now, and what's next? The next thing is we already developed novel chips for many years. So this started already in the 2000s, and next steps are integrating what you need for data processing, for quantum information processing, like microwave resonators are already included, but also microwave sources will be the next thing to include, and data processing on chip, and so on. So this is the next step, and this is summarized here, and this is my last slide. In the roadmap of eleQtron, so we concentrate on two paths, two parallel paths. One of them is achieving as quickly as it is possible something that reaches into the quantum advantage regime, but is not necessarily scalable beyond. So that's these generations, Ruby, Emerald, and Sapphire. And in parallel, we develop all the integration necessary to scale up to really large numbers of highly precise qubits. So that's what we call Moonstone. And yes, and then we have lots of partners, interesting partners from industry, where we develop use cases, NXP and Infineon, with whom we work with regarding the chip production, and several government organizations. Okay, and yeah, finally, that's a summary. That's the chip that we just put in a vacuum apparatus together with Infineon. Infineon produced this chip, we designed it. And yes, we are also hiring people, and that's where I'd like to finish. Thank you very much for your attention.